Hello, welcome to the tutorial session 2. In tutorial 1 we considered the electrocyclic reaction. In this tutorial we will consider certain problems concerning the cycloaddition reaction. Now in the pericyclic reaction there are large number of problems that one can come across with respect to assignments and the final examination and so on. So this kind of tutorial sessions are going to be extremely useful to follow so that you can do well in your final examination as well as in the assignment problems. Let us start with problem number 1. The question is, identify the structure and stereochemistry of the product formed in this reaction. What is the mode of the reaction? This is the question. Now this is trans-cyclooctene undergoing a cycloaddition reaction with the ketene, in this particular case dichloroketene, under thermal condition. Please recall the dichloroketene cycloaddition reaction with olefins. It undergoes a suprafacial anterofacial 2,2,pi cycloaddition reaction. Therefore the answer is that the reaction involves the trans-cyclooctene as a suprafacial component and the dichloroketene as the anterofacial component, resulting in the formation of the dichlorocyclobutanone derivative, which is this particular derivative. Please note that the stereochemistry is trans in the olefin and that retains its stereochemistry as trans in the final product also, indicating that the suprafacial component is actually the olefin component in this particular case, and the ketene component is an anterofacial component as far as the suprafacial anterofacial components of the cycloaddition partners are concerned. Now let us consider problem number 2. There are three structures of the diene A, B, C are given here. They are all diastereoisomers in terms of the stereochemistry of the double bond that is given. Now among the dienes A, B, C, the question is which one will react faster and which one will react the slowest in a Diels-Alder reaction with maleic anhydride. Now write the structure of the product and the stereochemistry of the specifically the endoadduct arising from each one of the diene. Now these are all written in the transoid form, so one should transform the transoid form into the cis-oid form, which is shown here. Now if you look at the stereochemistry of this double bond, this is E and that is retained as E, and this bond is now a transoid bond and that is made into a cis-oid bond. Then again the trans stereochemistry of this double bond is retained as trans. In other words, by simply twisting this carbon-carbon bond alone, we come to this structure retaining the relative stereochemistry of these two double bonds as trans with respect to each other. So please don't make a mistake of changing the cis into trans and so on. You are merely changing the transoid into a cis-oid. That's all that's done in this particular transformation. Similarly, B is converted into the cis-oid form, which is this form, and C is converted into the cis-oid form in this form. If you consider all the cis-oid forms, in the molecule C, where the two double bonds are cis with respect to each other, in the cis-oid form that brings the two methyl in close proximity with respect to each other. So the two methyls are sterically hindered in the C form, so it would not like to exist in this particular conformation. Predominantly it will exist in the transoid conformation. So from the reactivity point of view, this will be the least reactive because the concentration of the cis-oid form is going to be bare minimum in this particular case because of the steric hindrance that is involved in the it's not only steric hindrance that is involved in the cis-oid conformation of the C molecule. In the transition state also, these two methyl groups will be in close proximity with the steric hindrance with respect to each other. Therefore, the fastest reacting one is the one where the two methyls are farther apart from each other. The slowest reacting one is where the two methyl groups are in close proximity to each other. This will have an intermediate reactivity of this kind. Now in order to ascertain the stereochemistry of the endoadduct, one has to carefully consider the relative orientation of the maleic anhydride, these two hydrogens to be cis. So those two hydrogens are cis in all the adducts. Only the relative stereochemistry of the endo comes from the fact that the endo addition product would involve this hydrogen pointing out and this hydrogen also pointing out in the endo stereochemistry. So this hydrogen and this hydrogen of the cycloaddition partners should remain as cis for the endoadduct. So in this particular case, this is pointing out and this also is pointing out in the endo approach is taking place. That would put the stereochemistry of these two hydrogens cis with respect to each other. Now in this particular case, the methyl is pointing out here. the hydrogen will be pointing out in the endoadduct. Similarly, the methyl and the hydrogen are cis with respect to each other. Finally, the methyl and the hydrogen are again cis with respect to each other in a different fashion in this particular case, because the two methyl groups are interior to the system in this particular case. So the endoadduct, there are two things that one need to worry about. The relative stereochemistry at these two junctions, which is governed by the stereochemistry of the diene. The relative stereochemistry at these two junctions, which is governed by the cis stereochemistry of the dienophile, and the relative stereochemistry between carbon 1 and 2 and carbon 3 and 4, which is governed by the endo approach of this thing. So one need to write the endo approach properly and see which are the hydrogen which are cis with respect to each other, which are the hydrogens trans with respect to each other in the transition state of this particular molecule. You can see here the two methyl groups are cis in the final product because they are pointing out in this particular case. Here one methyl is inside and the other methyl is outside. That would result in the trans stereochemistry of the 1,4 junctions here. Here again the two methyl groups are cis in pointing interior, so they remain as cis in the final product also as cis in this particular case. So these are the endoadduct structures arising out of the 3C. You consider carefully the transition state that is resulting from the endo approach, then you will be able to figure out the relative stereochemistry of all the three isomers which are diastereoisomers with respect to each other. Now the third question has to deal with the synthetic methodology involving a Diels-Alder reaction. The question is, suggest a suitable method for the synthesis of the following target molecule using Diels-Alder reaction in your synthetic methodology. Diels-Alder reaction, remember, gives a 4+2 cycloaddition product which is a 6-membered ring. So this 6-membered ring has to be generated by a Diels-Alder reaction. However, Diels-Alder reaction gives you a cyclohexene derivative, not a cyclohexane derivative. That means after the Diels-Alder reaction, some other chemical reactions have been performed to saturate the double bond into a saturated molecule which is a cyclohexane molecule. So now if you do a retrosynthetic analysis, if you form this ring by a Diels-Alder reaction, this would be the precursor Diels-Alder adduct that one needs to consider. This on hydrogenation would give you the double bond to be saturated as a saturated carbon here. Simultaneously, the cyanofunctional group can also be hydrogenated to give the primary amine which is in the target molecule, for example. This can be a Diels-Alder adduct arising out of butadiene and dicyanoethylene as the dienophile, for example. The Diels-Alder adduct is essentially a cis adduct, so you need to have a cis isomer of the dicyanoethylene to form the cis isomer of the product that is shown here. So the actual reaction is, take butadiene, dicyanoethylene, heat it, you will produce the cis isomer of this particular derivative. When you do hydrogenation using palladium carbon on palladium charcoal and hydrogen, or nickel and hydrogen, you simultaneously saturate the double bond to unsaturated system and saturate the C triple bond N also to the primary amine. So platinum nickel can also be used for this particular reaction. Now you cannot do a retrosynthetic analysis in this particular manner. For example, if you take a diaminoethylene of this kind, in principle the Diels-Alder adduct would be formed directly with the cis stereochemistry if you start with a cis isomer. However, this is not a very good dienophile, unlike the dienophile which is a dicyano substituted dienophile. Remember, in Diels-Alder reaction the diene is usually electron rich and the dienophile is electron poor. So we were deliberately avoided using this diamino derivative as the Diels-Alder dienophile. Instead, the precursor, which is the masked form of the primary amine, which is a cyanofunctional group, which is an electron withdrawing functional group, is used as the dienophile substituent in the dienophile in this particular case. So this would be a wrong answer, although in principle this reaction can take place. In reality, this is not a very reactive dienophile, so the reaction is not a very easy reaction to perform with the primary amine being present and so on and so forth. It's a lot easier to perform the reaction with the dicyanoethylene rather than this dimethyl aminomethyl ethylene in this particular instance. So one has to be careful when you do the retrosynthetic analysis to make sure that diene and dienophiles are complementary in nature in terms of their electronic character. The question is fairly simple here. This is a fourth question. Identify the product formed in each of the following reactions. The first reaction shown is an azide, phenyl azide and dimethyl acetylene dicarboxylic acid. Remember, phenyl azide is a 1,3 dipolar component of a 1,3 dipolar cycloaddition reaction. This is a 1,3 dipole component of the 1,3 dipolar cycloaddition reaction. The reaction essentially involves the cycloaddition of the azide to the alkene to give the triazole of the molecule. So the final product is N-phenyl triazole with these two ester functional groups substituted arising from the dipolarophile, which is dimethylacetylene dicarboxylic acid. The second reaction is, this is an alpha chloroaldoxime and its reaction with cis diphenyl ethene in the presence of triethylamine. Remember, this is a precursor for making the nitrile oxide as by the elimination of HCl one can form the nitrile oxide. In the presence of triethylamine, the elimination of HCl will result in the formation of the nitrile oxide. So it is a nitrile oxide cycloaddition reaction with cis-stilbene as the starting material. So the first reaction is the alpha chloroaldoxime undergoes elimination to give nitrile oxide. The nitrile oxide undergoes cycloaddition reaction with cis-stilbene. What is important is the cis stereochemistry of the two phenyl units, because this is a suprafacial cycloaddition reaction. With respect to the third phenyl group, a mixture of diastereoisomers definitely will be formed in this reaction, as it's not going to be a highly stereocontrolled reaction of this kind. Now this is a very interesting question. Suggest a method for the following conversion. In other words, you have to take cyclopentadiene, react it with whatever molecule that is necessary to form this particular product. Now a clue can be given to solve this problem. If you take a norbornene kind of a 2,2,1 bicyclic system and do the ozonolysis, the 1,3-dialdehyde can be obtained. The 1,3-dialdehyde will be a cis-dialdehyde because this carbon-carbon bond and this carbon-carbon bond are pointing in the same direction, resulting in the cis stereochemistry of the dialdehyde. So if you look at this target molecule, these two dialdehydes are cis with respect to each other. So all one needs to know is what kind of a starting material that one needs to take in order to do a Diels-Alder reaction to bring this component that will undergo ozonolysis to give the dialdehyde. You take this example. Suppose if you take this particular molecule and do the ozonolysis, this is the component that you will be forming during the course of the ozonolysis. The carbon-carbon bond, this carbon-carbon bond and the ester carbon-carbon bonds are cis with respect to each other. So all the four carbonyl functional group will be cis with respect to each other. So now the question is, how does one get this as a Diels-Alder product? This is clearly a Diels-Alder reaction between cyclopentadiene and dimethyl maleate as the starting material. So if you take dimethyl maleate as a starting material and react it with the cyclopentadiene, the endo-adduct is going to be the predominant adduct. This is an endo-adduct. The endo-adduct is important because that would put this carbon-carbon bond and this carbon-carbon bond cis with respect to each other. The exo-adduct will have exactly the opposite stereochemistry of the two esters being trans with respect to the two dialdehydes. So this is the first reaction. Once this reaction is over, ozonolysis will essentially give you the aldehyde diester kind of a molecule. One can use this strategy in an analogous manner to synthesize this particular molecule. In other words, all cis pentahydroxymethyl cyclopentane as the target molecule, starting from this as the Diels-Alder diene component. So please think about this problem very carefully and try to identify the starting materials that are necessary. One of the starting material is given as this molecule. The other starting materials you consider carefully and see if you can arrive at the synthesis of this particular molecule. I am not going to solve this problem. This problem is an assignment that is given to you. So try to solve this problem carefully using the same kind of a strategy that is shown for this. For example, if you take this molecule and reduce it with lithium aluminum hydride, you'll get 4 hydroxymethyl functional group. So you need to think about the 5th hydroxymethyl functional group coming from the already existing hydroxymethyl derivative that is shown here. So it's not a very difficult problem once you understand the concept of this particular problem to be able to solve this problem very carefully. Now, this problem has to deal with the mechanistic aspect of the Diels-Alder reaction. Suggest a suitable mechanism for the following reaction. Now this dibromo derivative, when you treat it with butyl lithium, first it will undergo a bromine lithium exchange, metal halogen exchange reaction, resulting in the formation of a lithium derivative which will undergo lithium bromide elimination to give the corresponding benzene derivative. So the initial reaction is the dibromo derivative undergoes lithiation followed by elimination of bromine to give a benzene. Once the benzene is formed, this is a diene. Benzene is a dienophile. So this diene and this dienophile will essentially undergo Diels-Alder reaction. So the Diels-Alder reaction between these two components is what is going to give this oxa-bridged bicyclic system of this kind. This is a oxa-bridged tetraphenyl substituted tetracene derivative is what is given as the final product, which arises from the 4-pi 2-pi cycloaddition reaction that is shown in the last stage of the set of equations that are shown here. Here is a problem where you need to identify what are the products A and B formed during the course of this reaction. You can see here this is a diene and this is a dienophile. So initially one can think of a Diels-Alder reaction between these two components. It takes place at room temperature in 3 days to produce A. So A should be the Diels-Alder product. Then A is reflexed in pyridine. In other words, it's reflected with the base. So it undergoes some kind of an elimination reaction probably to give B because there is halogen in this molecule. So what is the first reaction? The reaction is diene and a dienophile undergoing a Diels-Alder reaction to give this. Don't worry about the stereochemistry of the product because you are going to do elimination of this system. Only stereochemistry that you need to worry about this chlorine and the hydrogen that is present here should be cis with respect to each other, and the methoxy and the hydrogen that is being present here should be probably trans with respect to each other if it were to be a exoadduct, and cis with respect to each other if it is an endoadduct. So let's not worry about the stereochemistry of this, although stereochemistry is easy to predict in this particular case. Now this compound, when it is reflexed with pyridine, undergoes elimination of the hydrochloric acid. HCl is eliminated. Simultaneously a molecule of methanol is also eliminated, resulting in the formation of the aromatic system, which is the anthraquinone derivative that is shown here. So the structure of A is this with the halogen, and the structure of B is this one, which is an anthraquinone derivative in this particular case. Similarly, this reaction is also known where you have a dicarboxylic acid derivative of the ketene acetal that is shown here undergoing a Diels-Alder reaction. This is a double Diels-Alder reaction involving a Diels-Alder reaction. Two equivalents of this is used. One equivalent is consumed on the one side of the benzoquinone. The other equivalent is consumed on the other side of the benzoquinone. Then finally loss of hydrochloric acid, 2 units of hydrochloric acid and 2 units of ethyl alcohol is resulting in the formation of this particular product, which is the anthraquinone derivative. So this is an extension of the example that is shown here. One can perform with this as a diene and the dichlorobenzoquinone as the dienophile. A double Diels-Alder reaction, a double elimination of hydrochloric acid and double elimination of ethanol is what is going to lead to the formation of this particular product. Now again another question, identify the structure of A and B is what is given here. The answer is also shown in this particular slide. The structure A is this particular structure, which is an intermediate. It's a reactive intermediate because of the fact that it has an angle strain associated with this carbonyl sp2 carbon present in the system. It cannot accommodate 120 degree angle, which is the sp2 angle. Now initially a Diels-Alder reaction with alpha pyrone and the dimethylacetylene dicarboxylate results in the formation of this bicyclic derivative. The bicyclic derivative under the reaction condition is unstable. It loses carbon dioxide to form dimethyl phthalate as the product. So essentially one goes from alpha pyrone to a benzenoid derivative by loss of carbon dioxide during the course of the synthesis of dimethyl phthalate as the product in this particular instance. This is an example which has already been discussed earlier. Identify the structure of A and B in the following sequence. So this is a tetracyclone, in other words tetraphenyl cyclopentadienone. It is undergoing a Diels-Alder reaction with this diacetylenic molecule. In other words, 2 units of this can undergo, one unit can undergo Diels-Alder reaction here, another unit can undergo Diels-Alder reaction here, with the loss of carbon monoxide as indicated in this particular case, for example. So the initially formed adduct A would be a reactive intermediate, which is this particular intermediate. It is not necessary that this should survive under the reaction condition. This would undergo loss of carbon monoxide to give this particular product. The diacetylene molecular unit is shown in the red so that you can understand originally this was a triple bond. This was also a triple bond. It has undergone aromatization by loss of carbon monoxide 2 times from this adduct. to give this particular product. So A could be this and B could be this. It is not necessary that both the triple bond would simultaneously undergo Diels-Alder reaction. It could be a stepwise reaction. Initially this one undergoing a Diels-Alder reaction that eliminates the carbon monoxide to give this unit, and the second acetylene then undergoes the Diels-Alder reaction with the loss of carbon monoxide to give this particular unit. One can also write a stepwise mechanism involving two concerted 4-pi 2-pi cycloaddition reaction rather than involving one concerted 4-pi 2-pi cycloaddition reaction taking place twice in this particular instance. I hope this problem solving session was useful to you. You are able to understand certain basic concepts once again and apply it in the problem solving session as discussed in this particular module. Thank you very much for your kind attention.